Okay, thanks. Hi, everybody. So it's quite pity that I'm not there, but I would like to really thank the organizers for giving this opportunity to present the work online. So I'm Ahmet AVSAR. I am a lecturer in physics at Newcastle University, but in fact, I'm in a transition to move to National University of Singapore soon this fall. So I will be talking about black phosphorus spintronics. So I have one very general slides here, which shows that, as you know, that the traditional silicon-based electronic devices rely on the charge current propagation, but they are almost reaching their dimensionality and performance limit. So we had a crossover between the different technologies in the past, and the question is what we will be doing for the beyond CMOS. So my research is more or less like fitting into this big picture. So I'm mostly interested in the transport phenomena in solid materials, especially like the two-dimensional materials. Particularly, I'm doing exciton transport, spin transport, and some novel charge transport. But today I will be talking about the spin transport in a material which is quite exciting me. It's black phosphorus. So what I will be doing today is I will be giving a general introduction to the superior materials, which are showing quite excellent spin transport performance. And then to highlight also the importance of the black phosphorus, then I will be presenting the long spin signals obtained in these ultrathin crystals. And towards the end, I will be mentioning about anisotropic spin transport in this material. So, of course, before 2D materials exist, there were already quite successful studies on spin transport in other bulk materials. For example, in metals, the materials like aluminum, copper, silver were studied. And in these devices, there were quite good results. For example, most of these materials were already showing the spin transport at room temperature, but they had also a bit like initially some disadvantages, such as like short spin relaxation lengths and quite small spin signals. And then later on, by improving the device quality, it was shown that the spin relaxation lengths also could be quite long, and with the improved spin accumulation in this material. Similarly, spin transport in bulk semiconductors were also studied in materials like gallium arsenide, silicon, and germanium. So the initial experiments were again very promising. For example, in the semiconducting case, material case, spin transport performance in these materials were quite impressive, especially at low temperatures. Tens of nanosecond spin lifetimes were obtained, but it had also some disadvantages, and particularly it's quite low efficiencies at higher temperatures. But later on also, like by again improving the device quality, the spin transport was also obtained in this case in silicon by improving again the interface quality. So we had already, before 2D materials, we had already materials which are working quite well, almost with the room temperature operations, etc. But with the arriving of the graphene into the game, so the expectation was it will take the advantage of the both metals and semiconductors, particularly because it has extremely high mobilities, and the spin-orbit coupling in graphene is quite small, and there is also almost no hyperfine interaction. So all of these were translating into expectations of very long spin relaxation lengths. So the first paper came out from the Groningen group, so where they demonstrated room temperature spin transport with the spin relaxation lengths exceeding a micron. So which was quite positive, encouraging. And then later on again, by just improving the device quality, the spin transfer properties of this material also got improved quite drastically over the years. For example, a group in Aachen, they demonstrated the spin lifetimes in graphene. It can go from 0.1, 0.2 nanoseconds to the 13 nanoseconds by again just improving the contacts. So for now, graphene is the best material, is the material showing the longest spin relaxation length at room temperature, and it's better than the previous metals or the semiconductors. So this quite good spin transport performance was also demonstrated in large-scale graphene. Several groups already showed spin transport over 30 micron, 40 microns, etc. And some complex spin-based circuitry has been already started to be built, which is quite exciting for graphene spintronics community. So indeed, for me, one of the most interesting part of the graphene was, of course, it enables you to do all proximity studies that Sergio introduced very well yesterday. But beside, it's like monolayer material. Basically, you can tune its electronic properties by gate voltage. That's why 2D materials are indeed quite interesting. But graphene has some challenge because it's a semi-metal. Basically, it's both charge transport and spin transport properties cannot be significantly modified. So because of that challenge, first, what we did is we investigate in the bilayer graphene. Bilayer graphene is interesting material. So if you can apply electric field along the vertical direction in the device, you can induce a band gap. And what we did is, and of course, the device resistance is increasing slightly as you increase the displacement field. So the size of the band gap opening is quite small in bilayer graphene, but it exists. So what we did is we studied the spin transport while changing the displacement field in the material. And what we could see is we can turn on and turn off the spin current propagation in this material by increasing the displacement field. But the challenge was also, this only works at quite low temperatures. I guess in this case, it was around 1.4 Kelvin. So we have now several materials, semiconducting materials, which could be quite useful for spintronics, especially with the gate tunability. So black phosphorus is one of them. And I will be now showing a little about its spin transport performance. But first, let me just quickly remind you about the types of the measurements we are doing. So the typical spin wall measurement, what we do is we apply in-plane magnetic field to change the relative orientation of the injector and detector ferromagnet. And depending on the polarization direction, you have this rectangular shape spin wall signal, basically. In the case of the low fields, Hanle precession, what happens is you have also this precession term into the equation. So the spins, you are just applying quite low field so that you don't change the in-plane polarization direction of the ferromagnets. And under such small signals, the magnetic fields, the spins start to precess, and then we get this kind of spin precession curves, which we call Hanle curves as well. And the other alternative is if you apply high magnetic field, what happens is like you are forcing the polarization direction of the injector and detector ferromagnets in out of plane direction. So in that case, the spins that you are injecting are no longer in plane, so they are out of plane oriented. And in this case, again, you don't have any precession, but just the spin transport happens on your channels. So depending on the anisotropy in your material, basically this high field regime, it shows you a delta R non-local signal, which could allow you to extract the spin lifetime anisotropy. So this slightly different than what Sergio was showing, the oblique Hanle measurements on Thursday. So with this, you can use it, especially if the mobilities of the sample is slightly low, and especially if you are working at the high carrier concentration where you have really minimum nonlinear MR in your local charge transport measurements. So the basic pristine graphene characterization was we were always obtaining very nice spin wall signal, and the signal is equal to what we are also getting from the Hanle spin precession measurements. And graphene spin transport is quite isotropic, as demonstrated by Sergio's group through the oblique Hanle measurements. So we started with with the black phosphorus. Let me just give you a brief introduction. So it has this unique crystalline structure. It's puckered along the armchair direction, and the other edge is terminated with the zigzag edges. So the material has thickness dependent band gap. So its band gap is around 0.3 eV in bulk, and then it goes up to nearly 2 eV in monolayer case. So it's a quite unique material. It exhibits quite high mobilities, especially at the low temperatures, and room temperature mobilities of 5,000 was also obtained in this material. And because of this unique crystalline structure, it has a strong anisotropy in charge and Raman, etc. So, for example, in plane, the charge mobility along the armchair direction is nearly 2 times than the zigzag, and out of plane the direction is nearly 1/3 of the in-plane charge conductivity. So in black phosphorus, if you look at the periodic table, the phosphorus is just neighbor to the silicon. It's also a light atom, and silicon is quite a good spin transport channel material. So you would also expect more or less like a good spin transport from this material. And here, having like these different edges is not just affecting the diffusivity of charge or spin. It's also basically the effective masses along the armchair and zigzag directions are also quite different. So you would also expect a different strength of the spin orbit coupling fields along these directions. So you would expect anisotropic spin transport from this material. It's a centrosymmetric material. Basically, you would expect an Elliott-Yaffe type scattering mechanism. And especially considering having like such a long momentum relaxation times, you would expect also long spin lifetimes in this material. And another thing which is the phosphorus. It has a half nuclear spin, which distinguish this material compared to graphene or other good semiconductor, the good spin transport channel materials that I have discussed. So all of this could also indicate that basically we might have quite a spin-rich physics in this material. And we have done some black phosphorus spin valves. Basically, we encapsulated black phosphorus in between the HBN crystals, and the bottom HBN is serving as a mobility booster. So basically, it allows you to improve the mobility of the black phosphorus compared to the conventional silicon oxide substrate. And the top HBN, basically, it's serving as encapsulation layer because the material is degrading quite fast, and also it acts also as a tunneling barrier. And this is one of the optical images device that we fabricated. So we fabricate all these devices in the glove box environment. Therefore, the surface of these materials never got exposed to the air during the fabrication. So that's why we were paying quite attention to create a good interface in these devices. And while we were studying the basic charge transport properties of this material, we came across that indeed the area with HBN and without HBN top layer, it shows completely different transport curves. Basically, in non-encapsulated region, we have the N-type behavior, P-type behavior, sorry, and in the encapsulated region, we were seeing N-type behavior. And then we collaborate with the Cook-Yinks group from the US, and basically they figure out that the dipoles appearing at the HBN cobalt interface is reducing the effective work function of the cobalt. That's why now the Fermi level is more near the conduction band, which results in N-type conduction. And similar work function reduction in cobalt HBN was also shown by James Hong group from Colombia at similar times. Okay, so the first generation of the spin transport devices, we were seeing a clear spin signal, and the spin lifetimes that we were extracting from the Hanley curves were about 3 nanoseconds at 100 Kelvin, which was working up to room temperature. And the spin relaxation length in this device was also around 6 micron. And one thing that we could do with this material is study the spinal actuation mechanisms. And for that, we repeated these 100 spin precession measurements and charge mobility measurements as a function of temperature in multiple devices. And what we could see is that both the momentum and the spinal actuation times were scaling in good agreement parallelly over the temperature, which was kind of indication of the Elliott-Jaffet mechanisms. And we also got the ratios between the momentum, the spinal actuation times experimentally, and which looks quite similar to what Jaroslav Fabian's group have calculated for the spin mixing probability within the framework of Elliott-Jaffet theory. So the material shows clearly Elliott-Jaffet spin scattering mechanisms for in-plane spin transport. And the next thing that we were quite interested is studying the anisotropy, spin anisotropy in this material. So this time we start being more careful with the crystal orientation, and for that one we start to do the Raman on these materials to figure out the edge directions. So for example, in this sample case, what we found is this long edge was along the zigzag direction, and this one was this edge was along the armchair direction. So we put the ferromagnetic contacts in parallel to the armchair direction. And the basic spin transport, basic charge transport data shows that again the dominant n-type conduction in this material, but we do see the ambipolar behavior in this device as well. But it's mostly n-type material. We have also extracted the contact resistance and the device resistivity, which will be used later on to understand some of the material properties. So since this is a semiconductor device material, we first studied the electric field control of the spin transport in this material. So because the charge data shows that indeed the threshold voltage around 20 volt in this material, but the spin transport in this material was absent up to 40 volt. So it was not conducting even while the device is conducting. And later on, the spin transport just kicks in, and then we start to have the nanosecond spin lifetimes in this device as well. And then with the spinal acceleration lengths exceeding 4 micron, and then later on, the material again just show no spin transport. And this part especially was puzzling me quite a lot, because the device is quite conducting in this range, and it was quite strange not to see any spin transport. So we just did some simple MR calculations by looking into the FET and ERS spin diffusion theory. And basically here is the data, the last spin data that we could get, 62.5 voltage. So basically what's happening is the change of the device resistance and the contact resistance, the channel resistance and the contact resistance changes differently with the backgate voltage, and the MR percentage start to decrease beyond this regime, and that could be the reason why we don't see any more spin transport in this material. And next we studied the out-of-plane spin anisotropy. For that, what we did at first, we studied the low field Hanle measurement at high backgate voltages, so high carrier concentration regime, and we again obtain the nanoseconds lifetimes, and then we start to apply high magnetic field and to force the polarization direction of the ferromagnets to be out of plane. So, and this was the big picture of the data after the subtracting the nearly linear background, and what we see is the spin signal at the out of plane direction is much stronger than the in plane, so which was quite unexpected for us. And by just solving the spin diffusion theory to get this anisotropy by using the Taylor approximation in the first order, what we obtain is an anisotropy in the order of 5 to 6, favoring out-of-plane spin transport in this material. So for example, if we apply not negative but high field at the positive region, we do similar delta R signals, which is also making sense because the polarization, the directions for injector and detectors are parallel in both cases. And so it just gives it's quite surprising it was quite surprising for us. And then we start to discuss, is there like any really an effective kind of field which are forcing the spins to be stabilized along the out of plane direction? And then we also start to look at our spin valve signals a bit more carefully. And what we do see is basically, we do see like a spin depolarization type signal near the zero field in our devices, in the spin valve devices. And this is quite different than the regular graphene, what we see in the regular graphene spin valve signals. And we also check quite a lot. It has nothing to do with the background signal. And we start to look at the literature, and such anisotropy case was also obtained in the germanium-based spin valves in 2013 by the Applebaum's group. So basically, the argument is in an external magnetic field. They have G-factor anisotropy in this material, which is causing electrons to experience an additional field oriented along the Walley axis, and they discussed that this is the origin. So G-factor anisotropy was also expected for black phosphorus, but we are looking into the theory a bit more detailed now. And the other question was, do we have in plane spin anisotropy in this material? And for that one, we just compared the spin valve signals obtained from the spin valve signals and the spin precession signal. And as you know, in the case of the spin valve signal, the spins are just pointing into the one orientation, but in the precession case, they are experiencing the spin orbit coupling from all directions. And we do see like quite similar spin signals in both measurements. And sorry. And if we do just like a little calculations, despite having like a significant change in the anisotropy in the charge diffusivity, we nearly don't see any spin transport anisotropy along the in-plane direction. Okay, so with this, I hope I was successful in convincing you that the black phosphorus is a quite rich material for spin transport, and we have like nanosecond spin lifetimes, and we can control the spin transport by using the electric field. And indeed, if you look at the spin lifetimes obtained in the top spin transport channel materials, black phosphorus is also working quite well even at room temperature compared to graphene silicon, comparable to the graphene and silicon what was published before. And the spin signal, that the amount of spin signal we observe in this material is also quite high, which makes also black phosphorus quite interesting for particularly spin transfer torque studies for future devices. And with that, I would like to acknowledge my collaborators. So my master's student, Luke, who is graduating indeed today, and Prof. Barbaros Özyilmaz and his group at NUS, and the crystals were grown by Prof. Taniguchi and Watanabe, and we are strongly benefiting from the Yaroslav's and Martin's theory from the Regensburg. So I have also a short announcement. As I mentioned, I'm in the transition to move to National University of Singapore. I will have quite a lot of PhD studentship and postdoc positions. So if you have any students or who are about to graduate and looking forward to try a bit Asia, so I will be glad to consider. So that's all from my side. Thank you very much for your listening. If you have any question, I will be glad to answer.